Okay, let's dive right in. A few months back, you probably saw some pretty wild headlines flying around about Google's new quantum chip called Willow, and the claims being made, well, let's just say they were astronomical, suggesting a whole new age of computing was right around the corner.
But you know how it is. With every giant claim, there's always a ton of skepticism. So in this explainer, we're going to cut through all that noise and get to the bottom of one big question. Is Google's Willow chip a real, honest-to-goodness, world-changing breakthrough? Or is it just more fuel for the quantum hype machine?
So to really get what's going on here, we have to start with the claim itself. I'm talking about the absolutely mind-boggling number that made everyone sit up and pay attention.
Google basically set up this epic showdown. In one corner, its brand new 105-qubit Willow chip, and in the other, Frontier, which is literally the fastest supercomputer on the planet that we know of. The challenge was a specific test, and the result was, well, it's kind of hard to believe.
Yeah, you heard that right. Willow did the calculation in less than 5 minutes. Google's team says it would take that supercomputer, Frontier, 10 septillion years to do the same thing. That's a 1 with 25 zeros after it. I mean, that number is so big, the age of the universe doesn't even come close. It breaks your brain. And this really gets to the core of what they're trying to do. Hartmut Neven, the guy who leads the whole team, he's not just trying to build a faster computer. The goal here is to build a totally new kind of computer, one that can tackle problems we can't even dream of solving today. Things like designing new drugs from scratch, creating new materials, or even cracking nuclear fusion.
Okay, so a calculation that's quintillions of times faster. That sounds like a slam dunk, right? Case closed. But why are so many experts kind of shrugging their shoulders? To get that, we need to look at what Google's chip actually did.
And this is the real heart of the debate. The test they ran is designed specifically to be super hard for a regular computer, but, a walk in the park for a quantum one. So critics say, look, this is an artificial problem. It has zero practical use. It's like building the world's fastest car that can only drive on one specially built, perfectly straight road. Impressive, but you can't take it to the grocery store. And this quote from venture capitalist Francesca Ricciuti it nails it. Think about that ChatGPT moment. It's when this ridiculously complex tech suddenly becomes useful and easy for everybody. Willow, for all its incredible power, hasn't solved a single real-world problem for you or me. It's a stunning lab result, not a revolution in our hands.
And the skepticism doesn't stop there. Critics are quick to point out that we've kind of been here before, like back in 2019 with Google's Sycamore chip and the whole quantum supremacy claim, which other companies pushed back on. There are also big questions about the fact that these new Willow results haven't been independently peer-reviewed, and at the end of the day, 105 qubits is just way too small to do anything truly useful.
But, and this is a big but, if the flashy speed test isn't the real story, then what is? What's the thing that the actual scientists, the ones in the labs, are secretly fist-pumping about? Well, it turns out the headline completely buried the real breakthrough. And that breakthrough is all about something called quantum error correction, QEC. You see, the fundamental building blocks of these computers, the qubits, are ridiculously fragile. Think of them like soap bubbles. Any little vibration, a stray bit of energy, and poof, there's an error, and your whole calculation is ruined. And this, right here, has been the Great Wall of quantum computing for decades. The bigger and more powerful you tried to make your machine by adding more qubits, the more errors you got. It just became more and more unreliable. It was this frustrating catch-22 that made building a large-scale quantum computer seem almost impossible. But this is where Willow changed the entire game. The Google team figured out how to bundle physical qubits together to create a single, much more stable, logical qubit. And as they made that bundle bigger, going from a small 3x3 grid up to a 7x7, something absolutely remarkable happened. The error rate didn't go up, it went down. And not just by a little, it got cut in half. Then they made it bigger and it got cut in half again. This, right here, is the ballgame. This is the true milestone. For the very first time, an experiment proved that as you scale a quantum system up, you can actually make it more reliable, not less.
It's an achievement called going below threshold, and it's something scientists have been chasing, dreaming about for nearly 30 years. So, a massive fundamental scientific hurdle has been cleared. Amazing. So we can all get our personal quantum computers next Christmas, right? Well, not so fast. There's still a lot in the way. And honestly, I think this Reddit comment just sums it all up perfectly. This stuff is incredibly complicated, and the road from a cool lab discovery to a tool you can actually use is super long and filled with gigantic engineering problems. So let's just break down how far we still have to go.
Just to put the scale of this challenge into perspective, look at this. Willow has 105 physical qubits. But to do the really useful stuff like breaking modern encryption, scientists figure we're going to need a fully error-corrected machine with over 1 million physical qubits. That's not a small step. That's a monumental leap.
And it's not just about the numbers. How do you physically wire and control millions of these things? How do you keep a system the size of a building colder than deep space? How do you keep the qubits stable long enough to finish a calculation? And maybe the biggest question of all, we still need to discover the killer apps, the amazing algorithms that can actually use all that power. These are enormous hurdles.
So, after looking at the hype, the skepticism, and the real science underneath it all, let's go back to where we started. Breakthrough or hype? What's the final call?
And the verdict is, it's both. That 10 septillion year speed test, that's mostly hype. It's a great headline, but the problem it solved doesn't really matter in the real world. But the successful demonstration of scalable quantum error correction, that is an absolutely legitimate, crucial, and historic scientific breakthrough. It proves that the entire roadmap to building a useful quantum computer is actually possible.
And this is why it matters. Even if we're years away, this breakthrough is a critical step towards a future where quantum computers could help us design brand new medicines, create super efficient batteries, speed up the search for clean energy from nuclear fusion, and even unlock new possibilities in AI that we can't even imagine right now.
So no, the Willow chip didn't deliver a quantum computer to the world overnight. But what it did do was give us a crucial piece of the map showing how to get there. It proved that the destination is real. It's not a fantasy anymore. The journey is still going to be a long one, but for the first time, we know the path is real. The only question left is, when will we finally arrive?